Hello and welcome to HPart. Today we will be talking about PID controller tuning, and we'll be using minorsky, a free online workspace for PID controller design. Minorsky makes it easy for anyone to produce an excellently tuned PID controller, even if they don't have much experience. To see how, let's start by launching minorsky from the HPart website. Now that we have minorsky open, we need to learn more about the system that we actually want to control. So let's take a look at this picture. Here is the real-world system that we will control in this video. What you see in front of you is an embarrassingly dusty spectrometer sitting on top of a heating element. A spectrometer is a device which takes light coming in through a fiber optic cable, analyzes the different wavelengths that light contains. The purpose of the heating element is to heat the spectrometer to a constant temperature. Spectrometers are influenced by the temperature at which they are operating. So by recording at a constant temperature, we are able to get a much more reliable result. Now, those who are familiar with spectrometers will note that there are two ways to get a spectrometer to a constant temperature. One way is to cool it, and the other way is to heat it. Heating the spectrometer does increase your detector noise, but a heater is cheaper, simpler, and in many ways more robust than a chiller. And so I think the trade-off is worth it. Regardless, this is a controls video, not a spectroscopy video, so we're going to just focus on the controller. Now, from a controls perspective, there are a couple of challenges with this system. The first is that there's a long time lag between when we apply power to the heater and when the temperature sensor inside the spectrometer actually starts to move. This makes PID control difficult, and it especially makes manually tuning a PID controller difficult, because it takes about 10 minutes for this spectrometer to actually heat to the desired set point. And that's for a couple of reasons. The first is the delay, but the second is that you do want to heat it gradually, and you do want to limit the duty cycle of the heating element so that you don't accidentally overheat and damage the spectrometer. Now that we understand the system that we want to control, I'd like to talk about the high-level process that we're going to go through to control the system. The first thing that we're going to do is we're going to collect data on this system. Once we've collected the data, then we are going to allow minorsky to analyze it. Minorsky is going to do two things. The first thing it will do is it is going to fit a plant model for our system. That means it's going to look at our sample data, which is the duty cycle of the heating element and the output temperature of the spectrometer, and it's going to try to fit a known mathematical model to describe how the system is behaving. Once it has fit this model, it will then fit a controller to the model so that it can drive the model to accomplish the scenarios that we set out for the system. To put it simply, to use minorsky, what you want to do is collect actual data on your system performing. Then minorsky will fit a model to your data, and it will use that model to tune a controller to accomplish the desired scenarios that you set out for it. So that's where we're going. Let's dive into it. So we're going to go back to minorsky, and as we can see, the first thing we need to do is we need to upload our data set. Now, I've already recorded the data set, but I want to take a little bit of time to talk about how you should think about recording a data set for tuning in minorsky, because this is the most important part. What you want to do with a data set is capture the dynamics of the system so that you can understand how well the model minorsky has selected actually models the system dynamics. If you pick a bad model, your controller is guaranteed to be a bad controller. So a good sampling of your system dynamics is one that takes the system from a common rest point to a common set point, maybe incorporate some disturbances, and then lets the control go and allows the system to go back to wherever it was originally. At least this is the case with a heater. In general, though, you're looking for a data set that explores the dynamics of your system, particularly around the set point, so that you can fit a model that actually represents your system dynamics. To see that in action, let's upload the manual heater file that I recorded. Now, the first thing we have to do when we upload a heater file is we have to tell Minorsky what each column actually means. Now it is already identified that the first column is time and assigned it to t. It's also identified that the requested duty cycle is u, which is the controller output to the heater. And it doesn't quite know what smooth temp is. It has guessed that temp y is the plant output, but I'd actually like to use the smooth temp as the plant output. And I'd like to ignore the temperature. Now that I've done this, the data set is imported and validated, and you can see that this all changed. Essentially what this is saying is that Minorsky is already done. It has analyzed the data set, it has selected a controller or selected a model, and it has fit the controller. So in one way, we're already done, but that would be a short video. So I'm actually going to walk through all the different details of Minorsky so you can better understand the options that you have, and along the way, describe how we will analyze this particular model and fit that controller. So the next thing that we can do after we've selected each of these columns is we can select our fitting window. Now, it defaults to a full data set, but we could also decide to look at only a particular subwindow of the data set. Suppose between, I don't know, say 1,500 and 2,500 samples. So we could just look at this window. Now this would be a very bad choice because we're going to miss the actual ramp up in the heater and the time at which we had the heater turned on. This is the orange line is when the heater is turned on to a duty cycle of 0.4. The blue line is the actual temperature of our plant in centigrade. And these dashed lines show the window. Now when I manually recorded this data, what I wanted to do was turn the heater on for a long enough period of time that it would get up to a temperature near our desired set point. In this case, our desired set point is 53 degrees. Now, as you can see, my guess overshot the mark by about 2 degrees, which was fine. But I didn't just want in this sample model to get up to the temperature. I also wanted to show the decay, because the rise and the fall of the heater contain the necessary information to fit an accurate model, which would then allow us to fit an accurate controller. So I'm going to take the fitting window back to the full data set, and Minorsky will automatically recompute everything. So here's what we've got. We've got the period of time where I turned on the heater, waited till it got up to temperature, and then allowed it to cool. So this is our data set that we want to fit a controller to. Now the question, of course, is what controller do we want to actually fit? Well, because the system has already completed all the analysis, it's telling us what it recommends, which is a full PID controller. But you could choose to restrict the system to a P, a PI, a PID, or a 2 degree of freedom PID controller. For this, we're just going to stick with the PID controller for a couple of reasons. The first is that it works quite well. The second is it shows us how the derivative term can create some interesting dynamics in the system that we need to pay attention to. The next thing we need to configure are the output limits. Now, this is the default to automatically update from the data set, but I'm going to uncheck that so that we can manually configure this. We want our controller output min to be 0, that's correct, and max to be 0.4. As I mentioned, we don't want to allow a higher duty cycle for our heater because I don't want to overheat my spectrometer. As far as the plant output, this really doesn't matter too much, but the spectrometer could certainly get down to, say, 10 degrees, and it could probably get up a little hotter than where it actually is, so maybe 60. So I'm going to widen that out just a little bit. Now we go down to the next box, which is editing the merit function. The merit function describes how the controller is fit to the plant model. Now there are some basic presets depending on what you care about, but almost always you want to go for set point tracking, and I personally prefer aggressive set point tracking. I want to get to the set point and I want to stay there. Now you can use these presets, which affect the different weights of the merit function, or you can make your own custom one based off of a preset. But I usually find that set point tracking with an aggressive stance works well. The next section are the constraints. In the constraints, you can reject candidate controllers that don't meet certain criteria. For instance, you can reject controllers that overshoot by a percentage greater than you desire. You can also reject controllers that saturate for a longer time than you desire, and you can reject controllers that saturate the plant for a longer time than you desire. Most of the time, you will probably ignore these constraints, like I will in this video. The final configuration area are the situations. And these are, not surprisingly, the situations in which the combination of the plant model and the PID controller are evaluated against the merit function. That might sound a little abstract, so let's make it concrete. So here we have situation number 1. I've called it the nominal step. That's the default name. In situation number 1, we're starting with an initial plant output of 36.5, which is the initial output that was in our data set, 36.5 degrees. That's what the spectrometer started at. And we're noting that this situation is going to be used for both training and validation. So it'll be applied against the merit function, but we'll also get to see it at the end to see how we're doing. You can create situations for just training or for just validation, but it's usually sufficient just to have one for both. The next thing are the actual segments. Now we're going to definitely want to edit this. Initially, we're going to start at the initial plant output, but immediately afterwards, we're going to go to our desired set point, which is 53 degrees. The next thing that we want to adjust is the horizon. If we take a look at our data set up here, we notice that the dynamics of our system take quite a long time to evolve. So we're actually going to evaluate the situation all the way out to 3,600 seconds. And then the final thing is the weight. If you have multiple situations and you're using them for training, you can assign different weights to them in the merit function, which will determine how different errors in each situation are evaluated. So you might have one situation that's very important. You might give that a 0.8. And you might have one that you'd like to include but is less important, and maybe you get that a 0.3. Finally, if you wanted to add a new situation, you could do it just by clicking the Add Situation button, and then you could adjust it from here. But we'll just do it with a single situation today, so I'm going to go ahead and delete this one. You can tell that every time I delete a situation or change a value in the configuration, the analysis automatically requeues and reruns. And right now, we are ready to go. So let's go ahead and take a look at the analysis based on our configuration. To do that, we will click on the Analysis tab. This will open up the analysis. We can see some initial workflow status indicators, and then we can see that it's recommended a PID controller from a first order dead time plant model, and the control output peak was 0.4. So this is all nice to know, but the real meat is down in the plant section. So because I'm zoomed in for this video, it's kind of hard to see it all at once, but the controller that it selected was the first order with dead time controller, which had a fit of 88.86%. Now, if you take a look at the green line here in this plot, that is the actual output of the controller. As you can see, it's a pretty reasonable fit. However, it's a lot sharper at these corners than our actual plant. So the question might be, well, why did it fit it if there were other models that might fit better? The reason is this is just a simpler model, and the system generally will try to go with the simpler model if it thinks it's good enough. But just to see the other models that are not as good as the two-state thermal model, let's go ahead and start to click through them. The first is the integrator. Well, this one does not fit very well at all. The next one would be the integrator with lag, maybe a little bit better. Next is a one-state thermal. This fits reasonably well, but doesn't seem to be capturing all the dynamics of the system. Then a first order model, again fits similarly to the one-state thermal model. Next, a second order model. This is actually, I think, a better fit than the first order with dead time model in terms of smoothly capturing the dynamics, but doesn't seem to catch the peak quite as well. Next would be first order with dead time, which is quite sharp and that I don't really like. And then finally, the two-state thermal model, which is the best fit out of all of them. Now we can see this drops a little aggressively over here, and it doesn't quite reach the same height. But, broadly speaking, this is a very good fit. And you can see the parameters of the model are shown here in the plant summary table, along with the general mathematical form for this model and the actual fitted model itself. So actually, I'm pretty happy with the two-state thermal model, and I think we're going to use that for our actual plant to fit our controller. Now it's worth noting that every time we change the model that we want, the analysis gets requeued and rerun. So let's just go back to two-state thermal and use that as our plant model. Now we're going to take a look first at the fit residuals. You can see that we have a large error here. We're doing a pretty good job fitting on the ramp. We have another large error at the peak, and then essentially a very strong fit on the decay. Now, what you want to see usually for a good model fit, you can just tell visually, but you do want to see a residual that is balanced around 0, which is certainly what we have right here. So now we've talked about the residuals, let's move on to the controller section. Now this is the just general family form for our PID controller, and here is the fitted model. You can also see the different parameters that were used in fitting this model. And then finally, Minorsky will produce a JavaScript reference implementation with these parameters filled in. Now you can copy this directly into your application if you happen to be running JavaScript, or you can just pull out the parameters, or if you're using a coding agent, you can drop this as a text file and tell it to rewrite it into a language of your choice. So now let's move on to the analysis of our fitted controller. The first thing that we're going to be interested in are the Bode plots. Now, there are several different options for the units of the Bode plot. The default is actually radians per second, but I like to look at these slower ones in terms of period. So the first thing to note is our magnitude plot. And if we take a look at first the sections of the plot where the gain is very negative, this basically means that the open loop combination of our plant and our controller doesn't do very much with high frequency signals. It effectively rejects them. They get heavily damped. And this makes sense. Our heater is a slow system, and our controller is really only having strong control authority for low period signals, or long and slow signals essentially, with our 0 point crossing sometime around 8 or 9 minutes. And again, this makes sense because it takes about 10 minutes, we know, for the system to actually get to its set point. And the next is our phase Bode plot. Now again, the 0 crossing is also shown here. And we can see that we have a pretty strong phase margin of what was it up here, of about 78. Now, to understand phase margin, suppose that the phase right around the 0 crossing was around 180 degrees. This might make for an unstable controller if we were near 180 degrees, because with any small perturbation of our control in the real world, we might actually slip into a full 180 degree positive feedback loop, and our controller might cause our plant to become unstable. Fortunately, we have quite a healthy phase margin, so that's very unlikely to happen. Now let's take a look at our situation. Now if we take a look, we can see that our fitted controller is doing an excellent job of controlling the plant. We have a smooth ramp. We do not have a lot of overshoot. Only, say, what was it? About 0.1 degrees. And then it stabilizes. We also note that our time to reach the set point is about, call it 10 minutes, 11 minutes, which is then, for this, a very good time. And we notice that the controller settles into a smooth output of about 5.9% on the duty cycle. So this looks like an excellent fit. We're rising quickly. We're stable around our set point, or at least we're confident we will be due to the Bode plot. And yep, this is exactly what I would have wanted. Now that's all very well and good, but does this actually work in the real world? So what I've done is I've actually taken the fitted model that we got up here, right here, this reference implementation, and I've actually put it into the controller that controls that heater. And I like to show you the actual control trajectory for the controller that we fit. So to do that, I'm actually going to go back to Setup. Now let's go ahead and import the tuned controller. Now let's take a look. So the first thing to notice is that the PID controller, in terms of its outputted duty cycle, is fairly jagged. Now, the reason for this is that we're using a PID controller when the derivative term is very sensitive to calculation under noise. And our actual heater, you can maybe barely see it on this plot, but the granularity of the output of the heater is only 0.25 degrees centigrade, or a quarter degree. And so it moves up in a stair-step fashion. And even though we smooth the output, the derivative can still vary quite a bit, and that is what produces this kind of sawtooth output of the PID controller. This could be eliminated or reduced at the cost of adding increased filtering to make the derivative more stable, but this would also make the derivative lag more. And as you can see in the output of the plant, we were able to achieve an excellent control even though we had a rather erratic derivative. So let's talk about that control and compare it to what we saw in the simulation. So the first thing is, we reached our set point actually a little bit faster than the simulation predicted. We were able to reach it at around 578 seconds as compared to about 40 or 50 in the simulation. Next thing is that our peak overshoot ended up being about a quarter of a degree, which is very close to what the simulation predicted of 0.1 degrees. And also very impressive again for a temperature controller that only has quarter degree resolution. Finally, we note that after we reach the set point, we then drop a little bit to our actual set point of 53 degrees. We go down a little bit of about maybe 0.19 degrees before finally rising back up again to precisely our set point where our controller has stabilized. We'll also notice that the output of our plant controller is very close to the predicted output from our situation. Our steady-state output here is about 5.5%, and the output in our simulation was about 5.9%. So we can see that our control is behaving in a way that we would have predicted due to our situation. It's allowing us to quickly get up to our set point and stay there with an acceptable amount of error before stabilizing to a final output. Now that we've seen how minorsky can be used to take real-world data from a plant, in our case a heater and a spectrometer, and fit a controller, and then generate a successful control, I'd like to take a step back and summarize the steps to achieving this. The key step is to upload high-quality data that describes the dynamics of your plant so that a controller or so that a plant model can be accurately fit to it. Once we uploaded that, we decided whether we wanted to have a window on our data set or not. I'm just going to go ahead and re-upload the data. So we can see that we decided whether we want to have a window or not. We decided we wanted the full data set. Then we verified the controller family. We verified the output limits. We verified what we wanted for our merit function. And we created a situation that described what we wanted to accomplish with our controller. Once we had all of these in the bag, we then took a look at the analysis. We made sure that the plant model made sense. It did. We looked at the residuals. They looked good. We then considered the controller that the system selected, and we evaluated it by looking at the Bode magnitude to understand what frequencies it would respond to, and also the Bode phase plot to get a sense for whether the controller would be stable over the frequencies where it would have strong authority. Finally, we took a look at how the controller behaved in the simulated verification situations. After we did that, we went up, we took the reference implementation out, we put it into the actual physical system, And then we reviewed the actual output of the real system. And that's all it takes to fit an excellent, highly performant PID controller in Minorsky. Thank you very much for watching, and I'll see you next time.